Hey everyone, Sanjay Medichurla here, back with another computational methods video. This is a sequel to my part 1 video on coding the Jacobian in Python, and this time we'll be tackling part 2, explain and code a higher order function that returns functions that calculate the Frenet Serret tangent and normal vectors for a helical curve, and explain how the radius curvature can be obtained at any point along the helical curve. So, first thing we should probably do is figure out what this Frenet Serret is. So Frenet Serret, the formulas. Um, they describe the kinematic properties of a particle moving along a differentiable curve in 3 dimensions, right? And so if you've ever heard this whole TNB frame, tangent, normal, and binormal frame, um, that's what this is about. And so you have a curve, t, the tangent vector, and the normal vector, and b, the binormal vector. So physically, what do those mean? So this is supposed to govern a particle moving across, like a particle moving across a path, right? And so t, the unit tangent vector, is going to represent the direction in which the motion is occurring, right? And that's pretty self-explanatory. If you look at the particle here, at any point, the tangent line is going to be the direction in which the particle is moving. So the normal vector is perpendicular, the perpendicular to the tangent vector. And what the normal vector shows you physically is the direction in which the particle is turning, right? So if you look here, for example, like here's probably a good, um, the particle is going to be turning in the direction of the normal vector. And then the binormal vector is the cross product of the normal vector and the tangent vector. So they are perpendicular. It is on a plane perpendicular to this one, right? It's pointing out of the page. What does that mean? Physically, this one's hard to explain, but it's the direction in which the particle is twisting. So think about like a plane that does like a twist or like a dip. It's kind of like that. This one's really hard to visualize, but it's the direction in which like a particle is twisting, right? And so to actually code these, typically they take it on the basis of the arc length of the curve, right? And um, if your curve is parameterized, like how we have, let's um, let's go here. Suppose a curve that is given by r of t where the parameter t need no longer be arc length, the unit tangent vector may be written as the the derivative divided by the magnitude, and that's because it's just the unit tangent vector, right? And so for unit vector, we always derive by the magnitude, divide by the magnitude. So let's go back to our old function, right? And just to recap, this is what our curve looks like. And then we want to use closure, remember, to find these unit tangent vectors. So I'm going to define a function, Frenet Serret, and it's going to take in a function, right? So we want to return the Frenet Serret vectors. Return vectors given a curve. Um, and so we're going to define 2 functions inside it. Define t at a certain point. Define n at a certain point. And so what I want to do for t is I want to take the derivative of a function and divide by its magnitude, right? It's not so bad. So the first thing is uh, d. So f. Actually, let's not use the quotes because it ruins everything. um, okay, let's use. So we'll say df dt equals Jacobian, right? The Jacobian of um, f, right? Um, it's going to take the Jacobian of f at a certain point. Um, and then to find the magnitude, right, we call upon the JAX library, right? JAX.linearalgebra.norm. And so that's weird, but it's not actually like I know it says norm, but it's the magnitude, and we want to find the magnitude of df dt at t, right? Um, and then tangent is just going to equal df dt divided by the magnitude. And the same principle applies to the normal. Oh shoot, sorry. To the normal vector, because here the normal vector is just the derivative of the tangent vector. And you might say, Sanjay, I don't believe you. That can't be possible. Uh, why would they be perpendicular if they're derivatives? And so I'm going to do a quick proof here. It's a little bit outside the scope, but I think it's kind of useful. At least it'll help me understand. Right? So suppose you have a vector v and you take its dot product, right? If these v's are of a fixed length, right, then their dot product is going to be some sort of constant, right? And so if I'm going to differentiate these both sides, what I'm going to get is v prime dot v plus v dot v prime equals 0. And then commutative property tells me 2 v prime dot v equals 0. Sorry, this should be v dot v prime equals 0. Now, what do we know about two vectors that have a dot product of 0? That means they are perpendicular to each other. So in our case, it's perfectly valid that the tangent vector can be perpendicular to the normal vector, and that the normal vector is the derivative of this tangent vector. And that makes sense in our physical description as well, because the derivative of the tangent is going to be so the derivative of like the direction it's going is how that direction is changing, right? And that's going to be how it's turning, right? Because if we think about the derivative, it's the rate of change. So how a direction of something is changing is based on how it is turning, right? And so physically, that relationship makes a ton of sense to us, right? And then I'm going to do the same things here. I'm going to say dt. I'm going to, honestly, I can just copy this because reasons. And then I'm going to say dt, and then I'm taking the Jacobian of t. I'm going to take the Jacobian of dt, and then dt divided by mag. I should probably use this mag 1, and then mag 1. And then I'm going to say return normal. Oh, I forgot to return something over there. That's awkward. Return tangent. Yeah, return normal. And then here, return t n. Oh, this should be normal. Um, now, um, if I now what I can do is I can say how will I call this, right? I'll say tang norm equals Frenet Serret Frenet Serret f jax. Okay, yeah. So it should be the Jacobian version, right? Because we're calling a bunch of things that are using the NP, or the JNP. So it should be like this. I'm just gonna move that, and then f jax, and then let's find the tangent at 0 and the normal at 0. And let's run this and see if we get any errors. Oh, we're already getting errors. What's the error? Expected a callable value. Oh, sorry, this should not be specified. It should just be f, because you're finding the Jacobian generally of that function. My bad. And now what's wrong? Jax has no. Oh, it's JNP. It should be JNP dot linear algebra. Oh. It's just J and P dot linear algebra. Because it's not Jax. My bad. Because we imported it as J and P. We still have errors? For function and device. Oh, yes. Oh my goodness. I'm missing a lot today. So when you have the functions, right, we need to call it at a certain value, or else you divide a function by the way. Now this should work. Oh, it's outputting the end. So let me just say print. Print. Okay, now let's print these, see what they look like. Okay, and then so we get some value. We get some values for the tangent and then for the normal at 0. So um, at 0, it's saying that the it's saying that the normal is -1 and then the tangent is 0.99 and 0.132. It's pretty hard to visualize here, but if you look at the direction it's moving at 0, um, uh, goodness, this is very hard to work with. Okay, if we look at the direction it's moving at 0, it's like slightly, the curve is like slightly moving like a slanted way, which uh, sort of supports our theory, right? So it's kind of hard to verify these results physically, but we'll trust in our coding for now. And then the next part is explain how the radius of curvature can be obtained at any point along the helical curve. So the radius of curvature is just 1 over curvature, um, I think. Um, but how can it can be obtained at any point along the helical curve? So how do we do that? Uh, so what is the curvature, right? So the curvature can be thought of as like the rate of change of how much our function is changing, right? Because it's about its curvature is like the tightness of how it's turning, right? So you take how it's turning and then the derivative of that. So it can be taken as the second derivative of our function, right? Um, and so uh, it being the second derivative of our function, right? The tangent is like the first derivative of our function. So the curvature is kind of analogous to like our normal vector. They are very, very closely related. And in fact, they actually have like an inverse relationship, right? So our normal vector will just be the 1 over the curvature in the direction of the derivative of the tangent vector, right? And so what we can do is to find the curvature of at any point, we can find the normal vector and then take 1 over its magnitude, um, and we should get the curvature at any point along this helical curve. Thank you guys for listening, and I'll see you in part 3 of this video series. Thank you. Bye-bye.